It's an exciting time to be an asteroid researcher. Think about all of the missions that have just wrapped up, missions that are in the works, missions that are in the planning stages. You've obviously got OSIRIS-REx and Hayabusa 2 that have gone and visited Rubble pile asteroids. You've got the Lucy mission that it's on its way out to Jupiter's Trojan regions. We've got the MMX mission to Phobos. So there's a ton of interesting missions that are in the works right now. And what astronomers are finding is that the vast majority of these asteroids out there, the smaller ones, are rubble piles, that they are just piles of rocks held together by mutual gravity. And of course, one of the most momentous things that humanity has done in the last couple of years is changed the trajectory, changed the orbit of an asteroid with the DART mission. And we avenged the dinosaurs. So my guest today is Dr. Harrison Agrusa. He's a CNES postdoctoral fellow at the Observatoire de la Côte d'Azur, and he is researching rubble pile asteroids. Has worked on many of the missions that you're probably familiar with. Worked on the DART mission, is working on the Lucy mission, is going to be working on other upcoming missions, and has been analyzing just how these rubble pile asteroids work, how they spin up, how they gain moons, lose moons, migrate material, how we can defend against them, and what they might say about the formation of this sort of entire class of asteroids in the solar system. And it's really interesting. And the paper that drew him to my attention was about the fate of Phobos. You know, we know that Phobos is very close to Mars. It's going to eventually get torn up and crash onto the surface of Mars. But Harrison believes this might happen sooner than we think, and maybe has happened many times before. You're going to want to see the rest of this interview to understand that. All right, enjoy this conversation with Dr. Harrison Agrusa. Harrison, both OSIRIS-REx and Hayabusa 2 went to rubble pile asteroids. Did we know these were rubble pile asteroids before we got to them?
We probably had a good idea, right? These missions flew sort of roughly before my time. So, I wasn't involved in, when these missions were getting selected. But yeah, in the last, 30 years, the field has kind of undergone this big revelation that most small asteroids are rubble piles. So we think that all asteroids formed big, at a scale of roughly 100 kilometers. So most things that are below the size scale are collisional fragments from massive collisions. So you have two asteroids collide and they kick off a ton of debris, and this debris, reaccumulates as it's flying away. And so, yeah, everything that's more or less kilometer size or even, hundreds of meters, they're probably nearly all rubble piles.
Huh. And I mean, that sort of led to my next question. I was going to what percentage of these things out there are probably rubble pile? You're saying like most.
I would say pretty much all of them. There's, probably outliers. For example, I saw a recent paper. It's one of these LSST early release papers.
Right. I was just going to mention that.
Commissioning where they pointed this telescope at one point in the sky and took a bunch of images, and they discovered a handful of super fast rotating asteroids. And they're like almost a kilometer in size. They're like, I don't know, some of them are like 500 or 700 meters. And it had spin periods of like, I can't remember, like 10 seconds. These types of things, that's probably just a single shard, a single rock. But in our collisional models, we don't really produce things of that big intact fragments because we're just limited by the computational resources we have. We can't resolve these super small fragments in collision. So there's a bit of a mystery with those. Are they single fragments or not?
And so then if, the vast majority of these are rubble piles, what are the I guess the forces that are limiting them and sort of shaping their evolution over the history of the solar system?
Yeah. So the dominant thing is just their self-gravity. So they're just very loosely bound, debris piles, rubble piles. Other forces at play can be like cohesive forces, right, that hold them together. So if you have a lot of fine-grained material, you have van der Waals forces, for example, like the lunar regolith has a lot of cohesion. So cohesion could play some small role. But as we found when we've interacted with the surfaces, like the Hayabusa 2 SCI experiment where they made an artificial crater on the surface, or when OSIRIS-REx actually took the sample off the surface, when we interact with the surface, we realize that so much weaker than we expected. So these cohesive forces may not be playing much of a role. And so really it's just gravity and like basic friction sort of sets everything.
But then there are external forces, right? There's the heat coming from the
Yes, of
sun.
course.
There's the
Right.
rotation of the asteroid. There's interactions with another moon. How does that sort of play into their evolution?
Yeah, this plays a really fundamental role. So the reason, and it was a big mystery, like in the 90s, like why do we have near Earth asteroids at all? Because we know that their dynamical lifetime of any given near Earth asteroid statistically is like 10 million years. It's going to, be encountering the planets, and within 10 million years, it's either going to hit a planet, hit the sun, or get ejected from the solar system. So, and we know the solar system is over 4 billion years. So there should be no near Earth asteroids left, right? But they're coming from the main belt. So you have a asteroid family forming collision, a big collision that makes a bunch of small fragments. And then these fragments feel Yarkovsky forces. So they heat up from the sun, and they're also rotating. So on Earth, the hottest part of the day is like 3 p.m. because you've had all day long to absorb all the sunlight, and even into the afternoon, you're still absorbing some more sunlight, so you get a little bit hotter. So around the 3 p.m. location on an asteroid is where it's hottest, and so that's where it's emitting the most thermal radiation. And we also know photons carry momentum. And so the asteroid is preferentially emitting some momentum that is roughly parallel to its orbit. So the Yarkovsky force either adds or subtracts a little bit of angular momentum from the asteroid's actually orbit. So then it migrates. Its semi-major axis evolves. And so it can migrate inwards or outwards slowly over, million-year timescales. The big asteroids don't do this because they still feel the same forces, but they're so massive that it's negligible. The small guys, the 100-kilometer, 1 kilometer, these guys, they feel these forces. And so on solar system timescales, they migrate inwards or outwards till they eventually get to like a resonance with one of the outer planets, mostly Jupiter or Saturn. So these can be like mean motion resonances with Jupiter. So then they start feeling these resonant forces with Jupiter that causes their orbits to change more drastically, where they become more eccentric. So they become very elliptical. And now their pericenter is now going to start reaching down into the inner planets. Once they scatter once or twice off of Mars, they're now, in near Earth space. And so this is how we have a constant steady state of near Earth asteroids, right? We always have, some background level of collisions in the main belt, which are producing small asteroids, which then migrate to the resonance locations, which through Yarkovsky, which then interact with Jupiter, and then those start interacting with the inner planets. And so that's how we have this.
Can we settle this thing with Jupiter once and for all? People say Jupiter is your friend, that it is protecting us from asteroids, but would you definitively now say no, it's actually a bully that is sending asteroids inward?
In fact, it's not, because if you didn't have the planets there and you just had if you didn't have the outer planets at all and you just had the asteroid belt, you'd form all these small fragments, and they would migrate through Yarkovsky. So the small ones could actually migrate all the way down to Earth. Right. So you might still have some near Earth asteroids, but it would take a lot longer and it'd be a lot less efficient.
So I'm sort of imagining the sort of orbital mechanics of this in my mind. So you've got these asteroids, they're being heated, they're rotating, and they're absorbing energy, but then the point where they start to emit it is when they are like 90 degrees off of where they're receiving it from the sun. And so that's either putting a thrust in the direction that they're orbiting or in the direction against that they're orbiting. That's then raising or lowering their orbit, putting them into this, into this location where Jupiter and Saturn's gravity can get a hold of them and then force them inward, or they can just spiral themselves in. I didn't realize that the Yarkovsky effect sort of preferentially put things onto that 90 degree to
it's not quite 90 degrees. The force is one component of the Yarkovsky force is a long track. So it's either, adding energy or subtracting energy from your orbit. So it's not, totally 90 degrees. Some factor of it is pushing you radially outward or inwards. But in orbital mechanics, that doesn't change your orbit all that much.
Right. But then there's this other sort of effect that these forces will cause these asteroids to spin up.
Yes.
Right? They will spin up faster and faster.
Exactly. So there's the Yarkovsky effect, and then a very similar sort of side effect of this is the Yorp effect, which stands for Yarkovsky, O'Keefe, Radbieski, Paddock effect, which are names of the 4 people that kind of wrote some of these early papers. And this is a similar thing. So it's because all asteroids are somewhat irregular. They're not perfectly symmetric spheres. They absorb all these photons from the sun, and then they re-emit them as mostly thermal photons. But they don't re-emit them perfectly in a spherically symmetric manner. And so this imparts a small torque to the body. So the orbit is torqued, and so the orbit evolves, but at the same time, the spin state evolves. And so this Yorp effect will drive asteroids, it'll drive their spin pole to be either 90 degrees or minus 90 degrees with respect to their heliocentric orbit. So it'll make them perfectly prograde or retrograde spinners, right? And then also it will spin them up or down. And so
like if they're already going up, they're just going to go up faster and faster. And if they're going down, then they'll aim for 0 and then randomly pick their next direction.
And this mechanism is incredibly sensitive to the topography of the surface in a way where it's like hard. Like if you looked at an asteroid, I couldn't tell you like what's Yorp is going to do, if it's going to make it spin up or spin down. You can take like a synthetic like shape model of an asteroid, and you can numerically sum over all the facets and vertices and compute what the Yorp torque would be. But then if you change like one facet by a small amount, it changes the answer almost completely. So it's super sensitive. So there's also an idea that this could be somewhat like stochastic. Like you could spin up until you get a small landslide and a few boulders move on the surface, and then that changes the Yorp torque, and maybe you spin down. It could be this kind of stochastic process.
And so then what role do these rotating asteroids play with their existence of their moons?
Yes. So this is sort of one of the reasons why we think that a lot of these asteroids form moons through this effect. So if you're an asteroid that happens to spin up, eventually you're going to spin so fast that, self-gravity can't hold you together, and you're a rubble pile, right? If you're not a monolith, then what can happen is you'll shed mass. Kind of like, imagine if you're like you're spinning a pizza, right? Like in pizza dough. It's like this. So we see a lot of these fast rotators are sort of like top shape, like a diamond or, a little sort of flattened oblate spheroid, and they have a close-in moon. And so what we think happens is these things spin up to their spin limit, they undergo some type of failure event, and you get some maybe landslides, and material landslides down and picks up enough speed that material goes into orbit and then reaccumulates into a moon.
Wow.
So
and
that's
I also understand that it can migrate. So boulders will say lift off the surface, and then they'll find their way up towards the poles, and then now they can lose some of that momentum and attach back, and then the landslides kick them out to the equator again. And so there's like some kind of flow going on.
Exactly. And it's it's amazing. You would think naively, like you think, asteroids are really boring. It's just a rock in space, but they're super active in this sense, like geologically in ways that you don't get on a body with higher gravity, right? It's only in these special super low gravity environments.
It really feels like science. This is where science fiction has completely let us down and failed to catch up. That if you're going to make some science fiction show where people are going to be trying to navigate around an asteroid belt, and if you don't have all of the asteroids looking like rubble piles, then you have failed.
Yeah.
And of course, obviously, you also should only be able to see one asteroid at a time, maybe two, right?
Yeah. But it's super cool. These things just they spawn their own moons.
Yeah. And will they absorb their moons again?
Yeah, it's possible. So there's yet another radiative effect. So once you have a moon, there's another effect called the B-Yorp effect. B-Yorp, binary Yorp. And so the way you can think of it is the satellite is almost like an appendage of the primary. And so it can absorb photons and emit them. And that leads to the satellite's orbit with respect to the primary possibly migrating. And it can migrate inwards or outwards, and it's very sensitive to its shape. So it is possible that you form your moon. In most situations, tides are going to be pushing the moon outwards through tidal dissipation, but Bjork might overcome that and push the moon inwards until eventually maybe it gets too close to the moon, the primary, and it tidally disrupts and forms a new moon. or if it has enough strength, like if maybe the moon is just one big boulder, for example, it could go migrate all the way in and make contact with the primary, and now it's maybe a contact binary asteroid.
Right. And that explains some of the contact binary asteroids that we've seen.
It could,
right?
although most of the contact binaries we've seen have like a fundamentally different like overall shape than the binary asteroids that we've seen.
Mm.
And
so theoretically, you could have this process where these asteroids are spinning, these rubble pile asteroids are spinning, they are calving off a moon, the moon is drifting away, the Yorp forces are interacting, it brings the moon back, that it's just sort of evolving in this weird, amorphous blob over time.
Yeah.
You could come back a million years later and it doesn't have a moon anymore.
Yeah, exactly. And it's possible for, especially for near Earth asteroids, it's possible, like there's no evidence of this, but like, for example, Bennu and Ryugu both have this classic like top shape. They look like the primaries of binary asteroids, yet they don't have moons. So they could have had moons in the past and lost them somehow.
Right. And so with the DART mission, once again, both Didymos and Dimorphos are rubble piles as well.
Yeah. So this is exactly how we think those moons formed. Actually, after the DART impact, I led a paper on this, on how the moons formed, because now that we've seen one of these binary asteroids up close, there's a lot more like geologic context we can apply to these formation models, right? We see like on Didymos, this equatorial ridge. We also have craters on the surfaces, so we can estimate the surface ages. And so it's going to be hard for me to remember numbers off the top of my head, but I think we estimated that the surface age of Dimorphos is something like, I want to say like 100,000 years, but the surface age of Didymos is like 1 million years. So like a factor of 10. And so we had to explain how can Dimorphos be so much younger? And the idea is you can spin up Didymos and have it shed mass, and you form a moon that's the right size and everything. In this whole process can preserve most of the big craters like at the high latitudes of Didymos. So what we showed is you can shed mass, you form your moon without like ruining all your craters, because the craters record this super old age. And then Dimorphos would be much younger, and it hasn't had so much time to form lots of craters.
Yeah. Oh, it's really interesting. And so we're a couple of years now since the DART mission did its impact. Do we have a sense of what the results were? Were the dinosaurs avenged, I think is the first question.
Yeah, I think we demonstrated pretty robustly that we can hit the thing. We measured, how much momentum we transferred to it. I think in the future we could totally deflect an asteroid. It's just a matter of having enough warning time and having the budget to do it, I hope. I hope if we ever detect an asteroid that's imminently going to hit the Earth, then, we can afford to do a mission to do it.
But one of the worries was that these things are, because of this sort of loose sort of glom of material, that you blow it up or you smash something into it and then it just reforms itself and continues on its way. So, did that part work? Like, did we substantially change the orbit?
Yeah. So in this case, even though, what you described, in that scenario, you still would have transferred momentum to it. So momentum is still going to be conserved. You still transfer all your spacecraft's momentum. But yeah, to answer your question, so we hit Dimorphos, and very shortly after the impact, we were able to determine how we change the orbit of Dimorphos with respect to Didymos, because its orbit period is something like 12 hours, and we saw that change by roughly 30 minutes. So that's a really big change, and so it's very measurable. And so we knew that we changed the orbital velocity of Dimorphos around Didymos by something like 2 millimeters per second or something like that. Pretty small number. Now, the system, Didymos is much bigger. So the momentum we imparted changed the velocity of the system by a much smaller amount. And that took several years to accomplish the measurement. And the reason is because it's so small. So there was a recent paper that came out by Makati et al., and they used a bunch of techniques. They used both, the spacecraft images, ground-based observations and occultations, and they determined that we changed the velocity, the orbital velocity of the system by like something like 10 microns per second. So like less than the width of a human hair per second. And we measured that with meaningful error bars. It'd be like looking at the moon and measuring the speed of like a tortoise walking on the moon, right? It's so precise. And the reason why it took so long to make this measurement is because you can't you can't just look at the asteroid and perceive that it's going at a different velocity. You need years of that slightly changed velocity to add up and manifest in a substantially different position in space.
But theoretically, that would turn a hit into a miss if the timescales were large enough, and if we had the large enough impactor.
Yeah, exactly. When if we're having to divert a much bigger asteroid, then we would need more impactors or a bigger impactor, right? So, and this is, remember, we're talking about the change of the entire Didymos system. Didymos is something like 800 meters across. These types of collisions are quite rare with the Earth, right? What we're more concerned about in planetary defense are these like 100-meter sized impactors, because they're big enough that they do enough damage that we care about it, but they're also small enough that the impacts are frequent enough that we also care about it, like on human timescale, right?
Like every 1,000 years or so, we get hit by something like that.
We changed Dimorphos' speed by a much larger number, millimeters per second, still a small number, but not microns per second.
I think for the longest time, there had been these arguments about what was going to be the most effective way to prevent an asteroid hit on the Earth. Do you blow up a nuclear weapon nearby in a ablate material and have it act like a thruster? Do you set up a solar sail, or do you paint half of it white? All of these, try and create a boosted up Yorp effect or whatever.
Totally.
Does it feel now like just slamming mass into it at the fastest pace that we can seems sufficient?
I think so. I mean, maybe I'm biased because I was involved, right? So but it's the simplest. Like, why break it if it doesn't, or why fix it if it's not broken? Like, a kinetic impactor is so much simpler. Yes, I think a nuclear device would work, or painting it would work, but it's so much more complicated. And with the nuclear scenario, politically, it's more complicated too, right? So, a kinetic impactor, it works. And the momentum you transfer, we know, is going to be dependent on things like the topography of the surface and the material properties and all these things, which we may not know in advance. But the thing is, if you're designing a mission and you need to save the Earth, you're going to design for beta equals 1. So beta is this momentum enhancement factor. So, when you hit an asteroid, you transfer your momentum to the asteroid, but then you also make a crater and you kick off a bunch of ejecta, and that ejecta is going beyond the escape speed and is going in the other direction. So you get a momentum boost. So we know with DART, we hit it with mass times velocity of momentum, but we actually, in the end, transferred over 2 times that momentum to the target because we liberated all this ejecta pushing in the other direction. But if I'm trying to prevent, humanity from getting destroyed, I'm not going to design my mission like, oh, well, we better hope beta is 2.5, 2.4. No, you say beta is 1, and you send 2 spacecraft if you need a beta of 2, for example, right?
Right. So, but the point being, like, if the astronomers say, okay, here's the asteroid, here's the size, here's when it's going to hit the Earth, it's now a relatively straightforward math problem to go, then I'm going to need this much mass to hit the asteroid at this speed.
Like, we don't need to do any new huit just now becomes a massive engineering problem. Like, we got to build the spacecraft, operate them, and launch them, not miss, right? Which is a huge challenge. But from the basic science perspective, I think we have a pretty good sense of, we could deflect an asteroid if we really.
And I think that was the big, it feels to me like that was really the big unknown, was before the DART mission did its part. Like, here you got a rubble pile, which is essentially the worst possible scenario. And then, like, does your object just crash into it and just get absorbed like a sponge? Does it punch a hole right through? Would be almost the worst case scenario. So then
you don't get any of the momentum.
Then you don't get any of that momentum transfer. But no, it's exactly perfect. You get the momentum and you get the bonus of the thrust in the opposite direction. So So that's all in the right direction. That's great. You came to my attention because you wrote a paper about Phobos and sort of the far, far future of Phobos. We've mentioned here on the channel that Phobos is dying. What is the sort of the fate of Phobos?
Yeah. So one thing we know about Phobos is it will eventually be destroyed. So it's one of the few moons in the solar system that orbits within the synchronous limit. And so that what this means is the synchronous orbit is the orbital distance at which your orbit period matches the planet's spin period, right? So like geosynchronous satellites that orbit around the Earth, relative to one position on the Earth, they're stationary, right? So in the case of Phobos, it orbits faster around Mars than Mars rotates. So Mars rotates in something like 24 hours and 30 minutes, something like this. It's actually very close to an Earth day. But Phobos goes around in like 7 hours. So it's orbiting much faster. And what this means is that the tidal bulge that Phobos raises on Mars, Phobos goes ahead of that tidal bulge. So the tidal bulge is pulling Phobos back. So Phobos is slowly deorbiting and spiraling inwards.
Right. And speeding up the rotation of Mars.
Yes, by a very, very small amount.
Yeah. But in the reverse of what's happening with the moon. Like the moon is beyond that synchronous rotation period. It is drifting away and slowing down the rotation of the Earth. And Phobos and Mars is doing the opposite.
And so Phobos is unique because I think it's Phobos and then some of the inner moons of Neptune are the only moons in the solar system in this situation where they're spiraling inwards rather than outwards, and they'll eventually be destroyed.
Right. And literally, if you just measure the orbital height of the moon, what the day period of the planet is, that'll tell you whether that moon is going to crash or whether it's going to drift away off into space. Yeah,
exactly. Yeah. So we know it's going to happen. The question is like, exactly how long will this take? And the mechanism for exactly how it breaks up is still a bit of a question, but yeah, it's a certainty that it's going to happen.
Okay. Yeah. And so what were you trying to understand then?
So I was curious about, what is the distance at which it will really break up, right? So, if you take your classic like high school or college physics problem where you calculate the Roche limit, where you just calculate the acceleration on the surface and find the point where the tides and self-gravity cancel out, you might get something like 1 point, I can't remember now, like 1.2, 1.5-ish planetary radii or something like this. Another calculation you can use, I don't want to get too much in the weeds, but it's called like a Drucker-Prager yield criterion. The idea here is you calculate the stresses inside the body, right? So, or all the forces. So that you have gravitational forces pulling you inwards, tides trying to stretch you out, centrifugal forces because you're spinning, causing the body wants to, I guess, spread out too. You calculate all these stresses and you check like, do I exceed some criterion, and this criterion is based on material properties of the body. And if these stresses get high enough and I exceed that criterion, that means I break. I've been destroyed by tides. So that's as far as the math gets you. So, there have been previous studies that have estimated the tidal disruption distance should be something like 1.6 to 1.8 Mars radii. And this is based on assumptions about the material properties of Phobos, that it's actually would be a very highly cohesive body. Have a lot of.
It looks like a big potato, like a big rock.
It looks like a potato. But I think it's a rubble pile. I think it's just going to be a rubble pile. So there's two reasons for this. One, Phobos is 20 kilometers in size. It's right in that size range. Well, let me back up a second because I should give some context. A big question about the Martian moons is their origin, right? So they're thought to either be captured asteroids or like reaccumulated moons left over from a giant impact on Mars. I think in both cases, it's reasonable to assume they might be rubble piles. So if they're captured asteroids, most asteroids are rubble piles, and Phobos is in this size range. It's 20 kilometers. It's probably in that size range where it's small enough. It's a reaccumulated rubble pile. If Phobos and Deimos have reaccumulated from a giant impact, they probably, there's a sort of a debris disk around Mars full of a bunch of, I don't know, maybe meter-sized fragments, and these things gravitationally coagulated and formed the moons. And then they're rubble piles in that case. Um, so in that case, I think if there's not a whole lot of cohesion, then they're a lot weaker. And so what we did is we did some simple like analytic calculations and then some computer simulations to back those up, where I just simply calculated um, the accelerations you would feel if you're standing on the sub-Mars point on Phobos. So if you're on Phobos at the equator, at the location that's physically closest to Mars, where Mars would be like straight overhead, right? And so you have uh, tides pulling you away off the surface of Phobos. You have centrifugal forces due to the rotation pulling you away, and you have self-gravity pulling you down to the surface. So based on Phobos's, and I account for, the irregular shape of Phobos, it's not a sphere. So the gravity is not so simple. But anyway, these forces sum up to zero, so they cancel out when Phobos gets to like 2.2 Mars radii. So today it's at like 2.7. So this is like half a Martian radius farther away than you would have predicted based on models of like the material failure. So the idea I found is that you don't actually you can get to this point where like gravity at the surface is zero without the body formally like undergoing material failure. So you can have, if there's like loose boulders on the surface of Phobos, once you get to that point where gravity and all these forces cancel out, this material is just free to fly away without Phobos undergoing this violent, tidal disruption. So the thought was like, oh, well, this material is going to leave the surface. It goes into orbit around Mars, just like Phobos, and it's free to come back and collide with Phobos again at some later point in time. And these collisions would occur at much more than the escape speed of Phobos. So it's like the boulder gets stripped off the surface. Let's say like a month later, it recollides with Phobos. It's going to be colliding fast enough that collision will be erosive. So this one boulder recollides, it might kick off 2 or 3 or 5 more boulders, and then they do the same thing. And so the idea is that you don't need to migrate all the way in and go and undergo this big tidal disruption. You just need to get to the point where you can strip a few boulders and trigger like a runaway collisional erosion, where like Phobos is just destroyed by itself by boulders that it originally had.
And then all of that debris is slowed down by the atmosphere and rains down on Mars over the next.
Some of it would hit Mars, but I think, actually I haven't done like the calculation. I think some would hit Mars, but also I think a lot of it, you'd collisionally destroy Phobos until there's sort of nothing left, and you'd be left with like a debris ring, which could then reaccumulate into a new moon. So right. That's a possibility. And so that idea is
join Deimos.
Yeah. So that idea is not something new. So it's been proposed that Phobos is like a nth generation satellite in this like a, I'm trying to think of a good, like a ring recycling process.
Right. Okay. So like one of the weird coincidences that we happen to be present in the solar system at a time when Phobos exists.
Exactly.
And what you're saying is that if in fact this is a cycle, then you're always going to see some combination of moons. It's not special. Exactly. That's interesting.
Because our solar system is 4.5 billion years old, and Phobos is going to be destroyed in like 40 million years, which is very short in solar system timescale. So it's such a weird coincidence. So if you're uncomfortable with that, this is an appealing theory. So here's the idea.
I just felt very appealed. Yeah.
So the idea is, if you're within the synchronous limit, you migrate inwards, you get to the Roche limit, you're destroyed by tides or whatever, or this process I'm talking about, this collisional erosion thing, that actually doesn't matter too much. You get destroyed, and now you're a ring, right? Remember, you're still within the synchronous limit, right? The ring of material spreads out through viscous spreading. So some material migrates inwards and would reach Mars, and some migrates outwards, and it can migrate beyond the Roche limit, where it can reaccumulate into a new moon. Remember, tides want to pull you in, but while you still have this ring here, the ring actually supplies a torque to the moon and causes the moon to migrate out. And that can overpower tides temporarily until the ring dissipates and goes away. And once the ring is gone, your moon migrates back in, gets tidally disrupted, forms a new ring. And so this process might have occurred, 5 or 6 or 7 times or something like that over the age of the solar system. And so Phobos is just the last remnant we see today.
Oh, that's interesting. And so there would have been more material in the beginning
Exactly.
after the first impact, and then you've got this sort of cyclical process, and maybe Deimos is the leftovers that make it, because Deimos is farther than that synchronous rotation rate.
The synchronous limit is at like 6 Mars radii. Deimos is at like something like 7 Mars radii. So it's migrating outwards very, very, very slowly.
Right.
But it's beyond the synchronous limit. So Deimos has probably been there the whole time to witness this. It just Phobos,
capturing all the refugees. Yeah. That's really interesting.
So that's what sort of motivated me to look at this, because these previous studies on this recycling model go off this assumption that, you undergo tidal disruption like 1.6 Mars radii. And the closer you are to Mars when you disrupt, the more mass makes it to Mars. And so you lose lots of mass every generation. And so to explain Phobos today, you have to invoke a much more massive moon in the past. But if Phobos gets destroyed, or in like previous generations of Phobos get destroyed in this ballpark of like 2 or 2.2 Mars radii, then more mass makes it to the next generation. And so you lose less mass every generation. So it might just change the parameter space of like what size moon had to be there for this model to work.
Wow. That's really interesting. And I wonder, you must be wondering if something similar ever happened to the Earth.
Yeah. Well, in the case of the Earth, you need this synchronous, you need your moon to migrate inwards. So it actually requires a relatively slow rotating planet so that you can have something orbiting it close in that is going faster. In the case of the Earth moon system has a ton of angular momentum. So if you rewind the clock, and when the moon used to be much closer to the Earth was also spinning much faster. I can't remember exactly the numbers, but I think the Earth was probably, when the system first formed, the Earth was probably spending more like maybe 6 hours in a day or something like that. So there's no room in like the orbital space to stick a moon that's within the synchronous limit. So it can't migrate in. It's always going to be pushed out by tides. So this probably didn't happen for the Earth. But it could be happening for Neptune, for example. Neptune's got some rings, some moons. The moons are migrating inwards.
And then again, what were the chances that we would see moons in Neptune?
Yeah. But we don't know a lot about Neptune because it's so far away. We don't know a lot about all these moons, but they're super interesting. So I think
it would be interesting to see, sort of imagine what it would look like if Mars had rings. Yeah. To see that, the ring system around Mars.
It'd be super cool.
Harrison, a question I always ask my guests: what are you obsessed with right now?
Gosh, what am I obsessed with right now? I'm actually obsessed with cycling. So I was never a big exercise person, but in the last year I've gotten super into it. I live in Nice, France, which is to a lot of people considered the cycling capital of the world. I see when I go cycling, sometimes I'll see pro cyclists will pass me going so fast all the time. So I've gotten super into that. So I cycle to work every day up the observatory in Nice, up the hill. So it's really good exercise. So that's my obsession. I'm obsessed with all the mechanical aspect of all of it.
Yeah. My only advice on that is watch out for your hip flexors. I totally wrecked mine. I've been spending years recovering from mountain biking uphill to then do a downhill.
Okay, I'll keep that in mind.
So be careful. Yeah,
I'm starting to get to the age where I need to be serious about stretching and
and just if you feel this tightness in your hips, then you're probably starting to crank your hip flexors up. Yeah. But it's great. It must just be beautiful. How high up is the elevation of the observatory?
The observatory is I want to say something like 400 meters. So it's not super high. Because it's very close to town. The telescopes at the observatory, we don't do science with really anymore because you have light pollution and everything. But at the time it was built in the late 1800s, I think it was the highest elevation observatory ever built. It wasn't even that high, but before that, you wouldn't be able to haul materials up to the top of Mauna Kea and build a giant telescope, right?
Right.
So at the time, you had, took what you could get. So, yeah.
Yeah, but even so, if you get a good night, it must be a great view up there.
Yeah. It is really nice. It's an awesome view.
And that's Nice. That's the home of the Nice model.
Yes,
right? So
exactly.
A lot of kind of planetary
what I talked
work
about
down there.
with the Trojans and Lucy, the principal investigator of Lucy, Hal Levison, he came here in the early 2000s for like a sabbatical, and where that's like when the NEAS model was developed. So in one way, like the Lucy mission is like we're going to validate it. Basically, we're going to check. One of the prediction from the NEAS model is that the Trojan should be this diverse sample of all these Kuiper belt objects. So they should all be super unique and different, and because you're sampling, planetesimal formation at different regions of the disk, but they all got scattered and captured at this one point in time.
Oh, really cool. Yeah. It's kind of amazing that we're going to see some practical, like you have a theory, you make these predictions, and now a mission is flying to the Trojans, to the Lagrange points. Like this again, my audience is obsessed with Lagrange points.
Okay, yeah.
And so the fact that a mission is going to actually explore two of Jupiter's Lagrange points is pretty great.
And the orbit they designed to hit the Lagrange points is so cool too.
Yeah. Well, Harrison, thank you so much for taking the time to chat. Good luck with your research, and we'll keep an eye on Phobos.
Great. Yeah. Thanks for having me.
I hope you enjoyed this conversation with Harrison Agrusa. Now, we had a longer conversation where we talked about the Lucy mission and his work on this, which of course is going to be going to Lagrange points, which I know is catnip to the people on this channel. And so if you want to hear about the Lucy mission, what Harrison is going to be studying and analyzing, you're going to want to check out that longer version of this interview. So there is a link down in the show notes. It'll take you over to Patreon, where you can watch the entire interview with no ads. You don't have to become a patron. You can just watch it for free. So go and check that out. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Barely Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Balick, Darkfinger, David Gilton, David Mass, Evan.Bro, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org. Please follow my nephew at vbrick6994, Ray Kaidu, Richard Williams, Sean Sargent, Stephen Found the Money, Team 49, Telescopes Canada, Vlad Chiplin, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons. All your support means the universe to us. So this was a great interview for me. It filled a lot of holes in my brain about the sort of the nature of these rubble pile asteroids. And it's funny when you hear about this stuff after the fact, after the hard work, the discovery, all of the various factors have been thought about and considered, and you get to this place where the whole system is starting to make a lot more sense in sort of its dynamic process, that in fact all of these small asteroids are probably rubble pile asteroids, that they are shed from the impacts of larger objects, planetoids, things like that, and that there is this sort of constant cyclical nature of how these things operate, the way they spin up, they spin down, the way they calve off moons, absorb their moons, and how they migrate within the solar system. And it makes sense that this could also happen on Phobos as well. And it just shows you how much even just getting a glance at one of these asteroids tells us a lot more about it, and how important it is for us to have a lot more missions. And then when you consider even the larger picture, the fact that there are interstellar objects moving into the solar system, that each one of those could be studied. And so there's going to be a lot of work for asteroid